What is that in our sky? An extraterrestrial being, a spaceship, a comet, an asteroid, or something never seen before? These questions and more filled the heads of scientists when, in 2017, an unidentified flying object known as Oumuamua appeared in the Earth's atmosphere. But what exactly is it, and how does this discovery impact our world? Find the answers as we explore the arrival of space object Oumuamua, its uniqueness, and the possible implications of an encounter with Earth. Oumuamua's origin story. Are we finally being visited by worlds beyond our solar system? Has our blue planet finally been noticed by beings from other galaxies? Or is this just a fragment of a broken civilization that has found its way to us? These unknowns have worried scientists since the appearance of this unidentified flying object, which crossed the Earth's atmosphere in the fall of 2017. The Earth received its first interstellar visitor, Oumuamua, which translates as messenger from afar. But what makes it so special? This is actually not the first time that unidentified objects have visited Earth. Thousands of sightings of unidentified flying objects are reported each year, although some are false. But none have been as captivating and mysterious as this one. When we think about UFOs, we usually imagine flying saucers with extraterrestrial beings with oval heads and slender bodies visiting our planet. However, the reality of a UFO is broader. It is a term that covers any strange object not previously identified or catalogued, and that probably does not have its origin on Earth. It could be a space rock, debris from outer space, or even an alien ship if we tip the balance towards conspiracy theories. Now, with that out of the way, let's continue with our precious Oumuamua. The discovery of this interstellar object was a long-awaited event. For decades, scientists had predicted and anticipated such a momentous event to solidify our beliefs in the existence of worlds beyond our solar system, and now we have concrete, irrefutable evidence that the universe extends beyond the borders of our system. Solar. However, this story has an intriguing twist. Although scientists expected visits from other planetary systems, Oumuamua was not exactly what astronomers had in mind. Many scientists probably expected to encounter a large space rock, round or irregular in shape, similar to those we already knew. But Oumuamua is something very different. Its shape has aroused great curiosity. At first, astronomers thought it looked like a cigar or even a hot dog, but upon closer inspection, they realized it was shaped like a pancake. Furthermore, Oumuamua is relatively small, with dimensions of approximately 377 feet long, 364 feet wide, and 62 feet thick. Although this may seem large for an interstellar object, it is actually quite small. On October 19, 2017, astronomer Robert Warwick made an absolutely astonishing discovery. He probably didn't expect his day to end with the discovery of one of the most fascinating objects ever observed, but fate had something in store for him. Using the revolutionary Pan-STARRS telescope at the Haleakala Observatory in Hawaii, he detected this strange object crossing our atmosphere. At that point, 40 days had passed since Oumuamua passed its closest point to the Sun, and it was already 21 million miles from Earth, moving away from the Sun. To put it into perspective, that's about 85 times the distance between the Moon and the Earth. At the time of its discovery, Oumuamua was extremely unique, being the first of its kind ever found in our atmosphere. The International Astronomical Union initially designated it C/2017 U1, as it was initially thought to be a comet. However, since it had no tail, it was reclassified as 2017 U1, which ruled out its identification as an asteroid. Once it was irrefutably determined to have originated outside our solar system, the nomenclature changed rapidly. Colloquially it is known as Oumuamua, but scientifically it was designated 1I/2017 U1. The name itself reflects the belief that this object is a messenger sent from very distant places with the intention of communicating with human civilization. Critical information about the object's trajectory was obtained through the Pan-STARRS 1 telescope, which was part of the Space Guard's survey, and the Canada-France-Hawaii Telescope, CFHT. But that's not all. The composition and shape of Oumuamua were deduced thanks to the Very Large Telescope and the Gemini South Telescope, both located in Chile, along with the Keck 2 telescope in Hawaii. Oumuamua is relatively small and not very bright. Furthermore, since it was already several miles away from our planet at the time we noticed it, observing it turned out to be an arduous task. In fact, the object was not seen in stereo high 1A observations near its perihelion on September 9, 2017 because its brightness dropped to about magnitude 13.5 as it moved further and further away from Earth. By the end of October, its brightness had already decreased to an apparent magnitude of 23. In mid-December 2017, Oumuamua was moving too fast and was even too faint to be studied by the largest ground-based telescopes. Regarding the origin of Oumuamua, we do not have precise information about its provenance. However, the characteristics of Oumuamua have provided us with several clues about its origin. Apparently, it is an interstellar object, which means it has entered our solar system from interstellar space. The universe is incredibly vast and mysterious. Its size has fascinated scientists, philosophers, and curious minds for centuries. While the spatial size of the entire universe is unknown, it is possible to measure the size of the observable universe, which is approximately 93 billion light-years in diameter today. But what does this number really mean? To put it in perspective, a light-year is a unit of distance used in astronomy, and is equivalent to approximately 5.88 billion miles or 9.46 billion kilometers. This means that the observable universe is approximately 546.84 trillion miles or 878.58 trillion kilometers in diameter. This is a staggeringly large number that is difficult to comprehend. The answer to why the universe is so big lies in its origins. According to the Big Bang Theory, the universe was created approximately 13.8 billion years ago in an explosive event that caused its rapid expansion. Since then, it has continued to expand at an accelerated rate driven by mysterious forces such as dark energy. As the universe expanded, matter began to clump together under the influence of gravity, forming stars, galaxies, and eventually planets like our own planet Earth. Over time, these structures grew larger and more complex, giving rise to the incredible diversity of objects and phenomena we see in the universe today. The observable universe is just a tiny fraction of the entire universe, encompassing everything that exists. While the universe with a capital U includes all matter, energy, space, and time, the observable universe refers to the portion we can detect from Earth. This region is limited and extends to a distance of approximately 93 billion light-years in diameter. Light takes time to travel, so what we see in the observable universe are objects as they were in the past. Additionally, due to the expansion of the universe, distant objects are rapidly moving away from us, making them difficult to detect as their light is stretched and redshifted. The edge of the universe is a complex and fascinating enigma with no definitive answer. There are theories that suggest that the universe is infinite and has no discernible limit, based on the cosmological principle of isotropy. Another theory proposes that the universe is finite but curves around itself, without a defined edge. There is also the possibility that our universe is part of a larger multiverse, with other universes that may be connected or separate from ours. Furthermore, thanks to the James Webb Space Telescope, we have discovered the existence of the cosmic web, a large-scale structure made up of galaxies, filaments, and voids. This network reveals how matter is distributed and how galaxies evolve over time, arising from small fluctuations in the density of the early universe and amplified by gravity. Using the James Webb Space Telescope, astronomers have discovered cosmic web filaments in the early universe. These filaments were detected when observing 25 quasars, extremely bright galaxies with supermassive black holes at their centers, which existed shortly after the Big Bang. Among these quasars, A thread-like arrangement of 10 galaxies was found, anchored by a luminous quasar. These structures challenge our understanding of how the cosmic web forms and evolves, as they demonstrate that such filaments can exist early in the universe. Additionally, this discovery provides clues about how black holes may have influenced their environment at that time. The James Webb Space Telescope has made important discoveries studying the early universe and interstellar chemistry. It has identified the first strands of the cosmic web, revealing how galaxies and clusters form. In addition, it has detected for the first time the presence of a crucial molecule called methylcation in a planet-forming disk around a young star in the Orion Nebula. This molecule plays an important role in interstellar organic chemistry, and its detection confirms its relevance in the formation of complex carbon-based molecules. The discovery also provides insights into how organic molecules can form and evolve in protoplanetary disks under the influence of ultraviolet radiation. These findings demonstrate the sensitivity and resolution of the James Webb and its ability to explore the mysteries of the universe and cosmic chemistry. James Webb has revealed that galaxies cleared away the opaque gas of the early universe, allowing light to spread freely. This event, known as the era of reionization, marked a key milestone in cosmic history. Using the James Webb, astronomers discovered that galaxies existing 900 million years after the Big Bang ionized the surrounding gas, causing it to become transparent. Bubbles of ionized gas around these galaxies grew and merged, gradually transforming the universe into its current transparent state. These early galaxies also exhibited surprising features, such as active star formation and unexpected structures, challenging our understanding of galactic evolution. By studying these ancient galaxies, James Webb has provided invaluable information about their characteristics, masses and compositions, as well as their influence on their environment. These findings show how the James Webb reveals new aspects of the early universe that were previously hidden, allowing astronomers to deepen their understanding of the formation and evolution of galaxies. James Webb's Advanced Deep Extragalactic Survey (JADES) program is a leading initiative that uses imaging and infrared spectroscopy to study the evolution of galaxies in the early universe. JADES has made significant discoveries, including the identification of hundreds of galaxies that existed when the universe was very young. These galaxies, some of the oldest and most distant ever observed, provide key information about the formation of the first stars and galaxies. JADES takes advantage of the sensitivity and resolution of the James Webb in the infrared, allowing the detection of light from very distant objects that have shifted to the red due to the expansion of the universe. This approach has revealed galaxies at very high redshifts, demonstrating the power of James Webb to study the universe in its most primordial stages. The ancient galaxies seen by JADES are very different from the current ones. They are small, faint and young, with massive stars in formation that emit ultraviolet light that ionizes the surrounding gas. These galaxies are crucial to understanding how the first stars and galaxies formed, how they reionized the universe, and how it evolved from its dark state to a transparent one. JADES reveals complex and diverse structures in these galaxies, showing stellar activity, supernova explosions and mergers. It has also measured the size of nearby galaxies, showing us how they grow and change over time. With unprecedented sensitivity and resolution in the infrared, JADES opens new windows into the early universe and provides valuable legacy data for future research. James Webb studies galaxy formation by observing a protocluster of 7 galaxies that existed when the universe was young. These galaxies move at very high speeds within a halo of dark matter, which acts as a gravitational glue that holds them together. The James Webb used its near-spec instrument to measure the velocities and confirm that they are united in a protocluster. Additionally, he used spectral data to model the future development of the protocluster up to the present day, predicting that it will grow and transform into the coma cluster. This discovery demonstrates how galaxies clustered early in the history of the universe and how they evolved into the massive structures we see today. It also highlights James Webb's ability to detect and study faint and distant galaxies in the infrared. James Webb studies the formation and evolution of galaxies by observing their shapes and structures at different cosmic moments. In early galaxies, he discovered complex, chaotic structures that underwent rapid growth and transformation driven by gravity and interaction with gas. In more mature galaxies, he revealed more regular shapes and structures, indicating growth and change over time. He also found even closer galaxies with morphological diversity, but similar to those in the nearby universe. These discoveries demonstrate the variability in galaxy formation at different times and how James Webb resolves details in distant galaxies, revealing their morphology and complexity. In addition, the James Webb has made it possible to study the chemical properties of distant galaxies, revealing information about the formation and evolution of complex carbon-based molecules. For example, he has detected a carbon molecule called methylcation in a planetary forming disk around a young star, providing clues about interstellar organic chemistry and how molecules can form and evolve in cosmic environments. The James Webb has expanded our knowledge by detecting weak signals from distant and complex sources, validating its sensitivity and resolution in the infrared. These advances in the understanding of galaxies and cosmic chemistry are made possible by James Webb's unique ability to observe at infrared wavelengths and reveal hidden aspects of the early universe. The James Webb has revealed new details of the Pandora cluster, a complex and violent region of the universe located 3.5 billion light-years from Earth. The telescope has detected hundreds of distant galaxies and gravitational lenses in the cluster, amplifying their light and revealing their presence in the image. Additionally, James Webb has studied the distribution and composition of gas and dust in the cluster, revealing information about the temperature, density and metallicity of the hot plasma and cold dust. It has also observed the diversity and complexity of the galaxies in the cluster, showing a wide range of shapes, colors, sizes, masses, ages and histories, as well as signs of star formation, supernova explosions and mergers. These new details provide a more complete understanding of the evolution and interaction of galaxies in the Pandora cluster.